Hi, today we will see like different file formats in FEMFAT which are used in FEMFAT or which are generated during the analysis and the results file also. So first is the .bdf file or any other input file. So that contains our FE information and which we just input it our in FE entities. So it will identify this nodes, elements, sports, etc. So we will check once now what is CID file in FEMFAT. So it is check input data file. So if you go on and hit like check input data, you will have like the input data, what is there, and how many number of nodes are there in your model, and how many number of nodes material has been assigned, and if there are different materials, it will show up here. And the options you have chosen, the max stress, the min stress, everything will be there. So if by chance if you have closed the FEMFAT, you can don't worry. This file will now be generated. You can go here and there will be .cid file. So you can go here and see this data even after when you have closed the FEMFAT. So this is that CID file. Next is the .csv file. So .csv file is generally used in Channel Max. We will see in the later videos. So how to use the channel max, but for the time being if there are different loads versus time conditions or different loading conditions or stress time history, you can go here in channel max and in channels you can define that. Then is the .dma file. .dma file, as we have already discussed, is the output file for the post processor for different post processors. So we can even choose uh, what we want in our DMA output, and we can have in the hypermesh results or Nastran OP2 results anyway. Like in Patron, we can open the .dma file, or in ANSYS or in any other post processor. You can do it. So it is a basically it is a third party uh, FEMFAT results we want to see in third party post processor. We can see it. Then .dbs is .dbs is like we are not discussing it here. It is related to weld, so we will see it in some other video of weld in the next upcoming videos. .esp file is again related to sports, so we will not be seeing it. We will not be discussing in current video. And then .ini file is again very important file. If you want to go here, if you want to change your settings, FEMFAT input settings, you want to change your memory settings in FEMFAT, we will use the .ini file. Basically, if you want to go on here and edit the maximum number of nodes, maximum number of elements, there is some limit to it. So if you want to change it, you can change this it while at the starting, and also you can use the default if majority of the times you are using with abacus, you can choose abacus, and paths also you can decide your material database path, other things. Next is the .ffd file. .ffd file is nothing but a material database file. So you can just go on here in material database and you can just create your data of material. Sorry, just create some data and go on, and then you can export this data, and then it will be there in your directory as .ffd file, and that you can again go on and import it in your analysis, or you can share with your colleagues. So this is the use of that .ffd file. Next is the .ffj file. So once if in any process, like in whatever you are doing in FEMFET GUI, it will be recorded as a TCL script. So you can just go on and if you want to just go on and save this session, you can just go on and click on this icon or this icon. This icon will save as this femfat underscore one .ffj, or this will be saved as some other format if you want, femfat new .ffj. And once you open this file, uh, you will have a lot of commands. You will have all the commands whatever you have used it in FEMFAT, and you can again open a new FEMFAT and you can just run it, so it will again solve the same things. So you can even edit this we will see in some other video how to edit this, but for the time being this is like whatever goes on in the GUI will be recorded it in FFJ file if you want to save it. Then there is FMA, which is like the material assignment file. And then there is the FPS file. FPS file is the permanent scratch file. So permanent scratch file is nothing but this file which will go on as the results file. So you can open if you wanted, you can open it in the visualizer also. So I'm just calling it visualizer, and then I want, I can open the uh, visualizer .fps file. I can read the .fps file. This is how to do it. We will see it in some other video. But for time being, this is the use of .fps file. Very important file. So I'll close this visualizer. Next is the .fss file, which is like the FEMFAT scratch file. This is generally used in Transmax Channel Max. So this file is like the permanent is the temporary scratch file you can say, and same is with the FTS file. Now log file is, as the name suggests, it is kind of the log for whatever you do in the FEMFAT GUI. So basically there are two types of log file here. There is called .log and .parallel log. So .log will have some comments at what time you started and which menu you are going. It will be recorded as that. But .parallel log will not have any comments, and it will have all the commands, but it will not have any comments here. So this is the difference between parallel log and .log here. Then .max belongs to channel max, and .max t belongs to transmax. We will see in some other video. MP4 we will leave it. Message file is like the message file for any output errors or any kind of warning message it throws. It will be recorded in .message file. Then there is PNG. It's an image format. .profile. .profile is nothing but like the your detailed analysis in text format. So .profile, you can go on and like after the analysis is done, you can go on and check whether this analysis has went proper or not, like whether proper options are selected or not. So you can go on and check whether what is the stress multiplication factor used, and what is the material database used, and what will is the tensile compressive endurance limit and all. You can check here what are the options used here. Everything will be recorded in .profile, and even your stress data will be recorded for each and every node, and your damage is also recorded. So this is .profile use. Not .rfm file is also, we don't use it regularly, and .wdaf file. Other things are related to stream, so I'm not uh, covering in this video. Now .wdf file. If you have a seam weld data and you want to do the weld fatigue, you can go on here and read the .wdf file here from here. So this also we will see in the some next upcoming videos. So this is all about the files used in FEMFAT and what are the files it generate. I hope you find out this video helpful. You can go check out the playlist here of the FEMFAT. So thank you. Have a great day. Bye. Hi. So today we are going to see the use of influence factor, basically the blast option.
in FEMFAT basic, what is the use of this blast option and why to use it, and you should use it for mostly for 99% of the cases. I think you should use it. So basically, what is this blast option and why there are six types of blast, and why it is necessary to use it during the fatigue analysis. So basically, we will go back to firstly, we will go back to see what is newer rule to understand what is blast. So basically, there are two types of. Basically, sometimes what happens is like in actual scenario, like if we perform the fatigue testing and the material is going to the plastic state, then in our FE model, we should always use, uh, if you want to correctly evaluate the stresses, you should always use the plastic model, material plastic model. But sometimes those plastic models are not available with us, the plastic values, the stress strain uh, curve after the yield limit is we are not available with us. So at that time, what we do is we solve the model using linear material properties, and then we use Newber's rules to convert this linear stress strain into elastic plastic stress strain. So basically, once my FE model is solved, I have linear stresses, which are elastic stresses, which are much higher uh, magnitude. Then we convert it into elastic plastic strain, uh, stress and strain, basically using Newber's rule. So how the Newber rule use converts elastic into elastic plastic stress strain? We will see in the next slide. So basically, it assumes like the area under elast this area under stress strain when it is solved with linear materials versus the actual area under the actual stress strain. So this will be equal to this both area will be equal to each other. So on the basis of that, we will obtain using Newber's rule the actual stress strain after plastic after yield limit. So once this is done, so the Newber's rule is nothing but we are using this blast option. So, and now once you understand this, like why we use Newber's rule, and so we are solving our FE model using linear material properties, and we will use this stress strain rearrangement in blast option. Then you may ask like why if we have material non-linear properties also, then can we use in like in the fatigue solver? Yes, you can use it. You just need to switch it off. But I will recommend that even if you have those properties, then you should always focus to solve the fatigue problems to generate the FE results of the problems which you are going to solve in FEMFAT later words. You should always use the linear material properties. Why? Because most of the times, like when if uh, suppose this is the case, and this is stress string corresponding to two time signals. So suppose if you have solved for this one, for P load, if you have solved, we are most likely are not solving for the unloading time. Means, uh, yeah, 1 second. So means if you are solving, suppose this is load, okay, and and this is time, okay. So once you loaded this specimen, and if it crosses your yield limit, if the stress crosses your yield limit, when you go back. when you remove this load, your means there will be some residual stresses will be still be there in the specimen. So if it is crosses the yield limit, so then you also need to solve the unloading phase also. Uh, if you want to if you don't want to use the last option, and at many times we don't have the time to solve a second load step, that is unloading, and use it in FEMFAT. So for that reason, we always we if you have are performing pulsating cycle, you will just read the upper limit, and lower you will keep as you will not read anything in lower. That means it is zero, and FEMFET will automatically perform the unloading operations. What will happen when the load has been completely removed? What is the stress state at that, and use it in fatigue. Okay. So this we have understand uh, to use the blast option if we are using linear material properties, and we should always use this for 99% of the cases. Now in blast option also there are six kind of things like mean unfavorable sequence influence, mean without sequence influence, mean plus amplitude favorable sequence influence. So what is this? Firstly, if what is mean and mean plus amplitude? So you should always use mean plus amplitude unfavorable sequence, because if you use only mean unfavorable sequence, then what it will do is whatever the mean stress uh, whatever the mean stress you got from this time signal, or this stress strain curve or stress time curve, mean is equal to, so it actually we are using linear material properties, so it will use uh, de Newber's rule to convert the mean stress into the equivalent mean elastoplastic stress, but it will only convert mean, and whatever the amplitude you got it from the linear uh, material properties using the FEM of linear material properties, that will not be converted, but in actual reality both mean and amplitude will be converted. So that means we need to always use these options. And then what is unfavorable, favorable, and without sequence influence? So without sequence influence is just well understood that this cycle, these are two different fatigue cycles, but this cycle will have no influence in this cycle. Like there will be some residual stress at this moment when you start the new cycle, but if you don't use sequencing effect, then it will it will treat it like this is a new specimen, and there will be no residual stresses. So now again, what is favorable and unfavorable, one may ask. So if you are using unfavorable, then there will be something called as positive residual stress states. That means the tensile stresses from the previous cycle will be carried forwarded to the next cycle. So as we all know from the fatigue theory, that tensile stresses are actually causing more damage, and compressive stresses less improves the fatigue life, and tensile stresses worsens the fatigue life. So positive residual stress states with unfavorable sequencing effect is always useful. Means it always gives the worst fatigue life with worst case scenario. And you can also use the favorable sequence effect, but it will again use the negative compressive stresses. So negative compressive stresses will improve my fatigue life. Only chance if this case is worst is when you have a compressive cycle. Means your load is negative. Means your stress state is compressive in both. Like it is ranging from suppose minus 200 MPa to 100. to minus 100 MPa. At this time, favorable sequencing effect might be giving minimum life, but in most of the engineering scenario, whatever we solved, in most of the practical cases, uh, this will have always the worst life, unfavorable sequence. So you should always uh, select these options. So if you have any queries, you can write it in the comment box, and I will be, if I know the answer, I will be able to reply those. Thank you, everyone.
Hi. Suppose so we want to calculate the block cycle fatigue for this load cases. In step 1, it is like alternating load of P in vertical direction for 300 cycles, then 2P in vertical direction for 200 cycles, and finally there is 4 times of that P load for 10 cycles. Then we know that how to calculate the cumulative fatigue. You can use it 3 steps, and then you can put the factor amplitude and factor mean and the number of cycles, as we have discussed already in this video. We have discussed already in this video, so you can watch it. But the problems comes if this is a highly nonlinear system, then the scaling of this results of from the Abacus ODB or ANSYS RST or Altair uh, OptiStruct S3D file might not be scalable, because this might be a highly nonlinear problem. Then what to do? Or suppose if it is a linear problem itself, but the direction of loading is different, then suppose for this case, if it is a pulsating load of P to 0 load in vertical direction for 100 cycles, and then it is 2P to 0 load in axial direction for 500 cycles, then how come you can calculate the cumulative fatigue? So this for that we are still going to use the Minor's rule of cumulative fatigue by adding the damages. We can use the transmax or channel max here, but we are going to use basic here, and we will use a third party tool called Altair Hyperview to basically add the damage. So basically I will use this vertical ODB file which corresponds to this stress state, and I will solve it individually for I will check how many cycles it will get. I am in It will write in vertical.dma file. Then I will analyze it basically. So it got analyzed, and the vertical.dma file is generated, as you can see here. Now I will change the stress state to positive load, which corresponds to this load. This is in axial direction. I'm going to check how many cycles it will take. So I will just everything is same. I will just rename this to horizontal, or maybe axial.dma. Let's check, see how many cycles we get here. So it got solved here. Now as you can see that I have two DMA files here. For this DMA file is here, and this is called as vertical DMA, and this is axial DMA. We'll check what is the result of vertical DMA in Hyperview. Let me load this file, IMP file, and I will use it vertical DMA. Let's check what is the life I'm getting here. So 1 by damage is nothing but life in FEMFAT, and as you can see that I am getting a life of around 1 e power 1.7 e power 5, and I will also use this in the side. I will open axial.dma. Uh, so I will also check this. What is the life here? So as you can see that it is 1.3
37 e power 7 in in axial load, and yeah. So in vertical load, I'm getting 1.7 e power 5 cycles, and in axial load, I'm getting 1.3 e power 7 cycles. So now how to add this? So means how to find out the cumulative fatigue cycles. What is the block cycle in this case? So I will again use the minus rule, which says like you can basically add the damages, and if it is equal to 1, then means failure occurs, and if it is less than 1, that means the component is safe. So I will calculate the damage, and then I will just put 1 by cumulative damage to find out the fatigue block cycle here. So what I will do here in Hyperview, let me open this fresh now. So I will just open both files here. So I am going to this icon. I will delete this existing file. Now I'll just load both DMA files, and this can be applied to the n number of DMA files. N number of damages can be added, and we can get the reciprocal again. So I have loaded both, and let me click on apply. So once it got applied, now I'm basically I need to go to results here, go to derived loads step. Now I will go to type. I need to go to linear superposition. So basically I will just use the minus rule here. So first is axial DMA. So axial DMA, I am going to for axial load of 500 cycles. So I will put a scale to 500. Okay. Now I need to go to vertical DMA. Vertical.dma, I am going for 100 cycles. So I will put here 100. Okay. Now click on OK. Now go to third load step, that is derived load case, and go to here. Don't plot live fatigue 1 by damage, as 1 by damage can't be added. Only damage can be added as per minus rule. So I will click on apply. So this is the damage pattern. Now I will export this result to a D. I will export this result to a HTTP file. Once it got exported, then I will clear this session, and now I will open the HTTP file which I exported. Now this already contains damage which we plotted in the last just few seconds ago. Then we will go to results again. We will go to derived results now. We will calculate we will create one variable which is fatigue cycles, and I will insert this damage, and fatigue cycles is nothing but 1 by damage. So 1 by damage. Okay. Now once this variable is created, I am going to plot this variables. So yeah, so you can see this min life is coming out to be here, which is around 1746 cycles, block cycles, and it is, so that means it can already pass this load almost 1700 times, then it is going to fail. So this is how you can calculate the block cycle fatigue. If the loads are non-linear, if both loads are different in nature, or your structure is too much non-linear that the scaling of loads is not valid for a non-linear structure. So this is how you can calculate the block cycle fatigue. Thank you. Hi. Today we will see there is something called as damage calculation in FEMFAT, and there are basically five options here. We will look into these three options. These three options are generally used, and why we are In most industries, we are using setting minor as minor modified, and why so, and what is the difference between minor original, minor modified, and elementary minor. So basically, in most of the automobile industry, we are using minor modified, and why so. So firstly, before going to into this, we need to know the simple theory about SN curve and endurance limit. Endurance limit is like just like a there are many other limits like yield limit, ultimate limit. The material endurance limit is that limit if the amplitude stress is below the endurance limit and there is no mean stress, then it will go to the life of that component will be infinite. So in basic sense, if endurance limit when the mean stress is zero, if the amplitude stress is below endurance limit, then the life of the component is basically infinite. It will never break in the cyclic loading. So, but this is for the steel. For aluminium, if you draw the SN curve of aluminium, uh, firstly, what is SN curve? SN curve is nothing but a log of stress versus log of cycles, fatigue cycles curve. When the mean stress is zero, so this all tests are performed on the mean stress is zero, means there is like uh, stress is ranging from uh, plus sigma to minus sigma. Basically this means that, so in that case amplitude stress will be sigma and mean stress will be zero. Okay, so if you so this testing has been observed in simple steel and aluminum test cases. For steel, it has significantly many times it has been shown that it is always a straight line mostly, and for aluminum, it never that straight line is most likely not be able we are not be able to found that straight line. So for our convenience, like this is a thumb rule of empirical formula mostly used to calculate the endurance limit. In endurance limit in steel is nothing but its UTS divided by 2, and endurance limit uh, in aluminum components is nothing but UTS its ultimate tensile strength divided by 3. That is a thumb rule. If you are doing hand calculation, then this might be useful. Now coming to, once we have understanding regarding this, coming to what is minor modified elementary minor and original minor. So original minor is nothing but whatever we have read in the textbook, like in the graduate level textbook. Like this is the slope, its slope is k. This is log sigma, this is log n, and for this is for mean stress is equal to zero. Okay, so this is amplitude of log of amplitude stress. This is log of cycles stress, and this is elementary minor. Sorry, this is minor original. Minor original is nothing but whatever we have read in the graduate level textbooks. So there is a limit, and generally for it is 10 to the power 6, 10 raised to the power 6, and after that is k is infinite, means this is my endurance limit. After that, it will go on into n number of cycles, the infinite number of cycles, if the stress is below this range. Okay, but we have seen that for aluminum this is not the case. So what to do for that, to accom- to account for these errors? And for steel also, for some alloys of steel also, this might not minor original might not be the case. So what to do in these cases? So for all cases, for our general significance, we are using minor modified. Why so? Because elementary minor, as you can see, that slope is it is constant, means whatever the slope here after and during limit also the slope is same. So there exist stresses uh, for zero. If you see this one minor elementary minor for almost near to zero amplitude stresses, you are getting some life. Means uh, this is like the very conservative case. Means it will give you very less fatigue life, which might not be correct. Okay, but this is very conservative. Okay, minor original is not suited for the most of the materials. So we what is minor modified? Minor modified means the slope up to endurance limit is k, and then there will be a slope change which is 2k minus 1, and then after that it becomes a straight line. This is ideal for most of the general materials. That's why we are using minor modified, and there are several codes which also refers to the use of minor modified. That's why we are using minor modified in most of the cases. Thank you. Hi, today we'll see how to solve the alternating fatigue in FEMFAT. So firstly, what is alternating fatigue is like when the stress versus time is like each cycle is like some positive value of stress, and in the next cycle it is sorry in the minimum value is negative value of that stress, like positive negative it is like that, then we can say it is a alternating fatigue cycle. So we need to calculate the life, and then I have solved like this two load cases. One I am fixing it here, and this is both steel material, and fixing it here. Here I am pushing this, and here I am pulling this. So and also this will scale to 50 to show you the animation. The stresses are of the level of 800 MPa, as I am using uh, I am using linear material properties, and why the stress is same as I am using Mises stress. So Mises stress is always positive. So I'm getting although this is tensile in nature and this is compressive in nature. Okay, so I'm using this session, and then I am using here this files. So firstly I will use this load this IMP file. So it has having node element count of 1000 and groups. As it is a single component, you can just define all uh, stress data. You can use upper stress. You can use this one. So it is having uh, 800 MPa of positive stresses, and you can use its factor also, but factor currently I'm not using it. We will use the factor in the maybe in the upcoming videos. We will discuss this factor. Okay, and lower you can use this nag load. So nag load is minus something, minus 800. Material, I am defining one steel material which is having UPS of 340. Let me define it. Okay, and then I'm using load spectra. Just create one new load spectra. Just I want to run it for one cycle and see the run it for one cycle and see the how many cycles it will undergo for the damage, for the crack initiation. Characteristics, just put all, and I am defining this steel, and I am as it is a machine component, so I am defining a smooth 60 micrometers. Surface roughness I am switching it on, and as I am using linear material properties, so I am using mean plus amplitude unfavorable sequencing effect. Technological significance, we can switch it on, this we can switch it on, and then damage will be minor modified. Analysis factor I want to calculate for all elements which is having less than this stress. Okay, output you can select hypermesh result, as I want to use it in hyperview, and then let me open hyper also. Okay, then I will just go to analyze all and check input data. Check input data, it will show you the amplitude stresses and unit stresses, whatever it calculated after using class top sum. Click on analyze. So once analysis is done, let me open this. Uh, sorry, let me open DTMA file, and here I will open the IMP file. Let it open. Okay, model does not exist. What where is the IMP file? Here it is. This is the DTMA file. Here it is. Okay, let it. Okay, so we will plot this damage. One by damage is nothing but the fatigue life. So as you can see that I need to reverse the scale to see it properly. So the red zone is the most critical zone because minimum fatigue life we are more interested in. You can use this dynamic tool and you can see that I will go to scientific now. Yeah, so minimum cycles I'm getting at this node it is 4.23 into 10 power 4, which is nothing but 42,300. Yes, 42,300. Yes. So this is how you can calculate the alternative fatigue. Thank you. We will see the use of this factor, apply factor in FEMFAT. So basically apply factor is used to scale the stresses. So we will see the general load case. Suppose if there is a block kind of thing and it is fixed with this and it is there are one cycle is there. It is the alternating fatigue load is plus P load to minus P load. As I have only solved for plus P load, I have solved only for plus P load here. Okay, so sorry, yeah, I have only solved for plus P load. So you can see that stress is 8 837 MPa. So I have only solved for plus preload and I don't have the time to solve for the compressive load. So what I will do here is I will just simply load this ODB and I will use the factor of minus 1 here and apply. So you can see that the stress for this lower uh, set has been changed to negative load. Okay. And suppose instead of this it is minus zero point 0.5, then again do the same thing. You can't just use the factor again as it will it will not scale the stresses correctly. So again don't override the factor. I mean to say, if you want to replace the factor, again read the same stress. It will update it to original, that is 837 MPa. Then use the factor. Then the factor should be zero point 0.5. Sorry, it should be minus zero point 0.5. You can't use the factor twice. You again need to read the stresses and apply the factor. So just do it. So upper stress is 837 MPa, lower stress is negative always. So in the same way, you can use this factor setting, but you can't override this. Again, if I want to apply this to 1, it will not take the 1, means it will override this. So there will be a discrepancy. So if I want to use it to some other thing, I will again open this ODE and I will use the factor. Suppose I want to use the 80% of the load. So 80% of the load is point A. So point A. So this is nothing but 1 plus P2 plus 0.8 and okay. So for which cases you can use the scale factor? I will not recommend to use this factor, stress scale factor. But for completely linear case like this case, you can use the factor, no problem in that. But for whenever there is a geometric nonlinearity or contact nonlinearity is there, then there might be issue of using this uh, factor, scale factor. The reason being is that the stress in the positive direction or negative direction, or the stress at 100% of the load and 50% of the load are not proportional to each other. You can see this example. Like suppose there this is the load I am applying 1000 Newton here. The gap here is from the fixed bars are is 3 mm. So here the deflection would be like the stresses it will generate in this direction if you apply this load will be less as opposed to if you apply in this direction, the opposite direction, the 1000 Newton, you will get more stresses. So it is always recommended to solve both upper and lower load cases separately in Abacus or in Nastran or anywhere instead of using the scale factor. But for completely linear cases or which are nearly linear, you can use this factor. Thank you. Welcome to Simulated Engineering. Let's start. A brief intro about FEMFAT on material data. So, like there is a we need material data to perform our fatigue analysis. That is first thing. Second thing is like there are different types of materials you can use here. You can create materials. Suppose I create uh, Fe410. That is some kind of steel. And then for if it is a steel, then what I will do is I will choose iron here, and if its ultimate is 410 MPa, I will choose a 410 and I will press enter. Through some empirical formula, it will automatically determine the pulsating alternating strength and yield values. And if you have yield values also, you can put it here. You can press OK. And if you have something like, what can I say, something like casted aluminium, okay, then you can use it here, aluminium, and then you can use aluminium casting alloys, and then ultimate, suppose it is having a 210 MPa ultimate, then you can press OK here. So this is how you can also create the casted aluminium material properties. So here you can see, uh, one second. Yeah, here you can see like it is having the ultimate of 210 MPa Newton per mm square, and Young's modulus is 70 MPa. Okay, for steel it is again it is Young's modulus is correct 210 MPa, and ultimate in strength is 410 MPa. Sorry, Young's modulus is 210 GPa, and aluminium Young's modulus is 70 GPa. Okay, gigapascals. Okay, and you might be thinking like, okay, I need to always create the materials. No, you are wrong. You can always export this material. Suppose I am exporting it here in my directory. Suppose I'm creating it ffj files. Okay, okay, and then you can create aluminium casted. Okay, so this has uh, exported it. I exported this and fe410. So these two files are exported. Okay, these two files are exported, and you can check it here. And how can you check this? So you can also check uh, in your text editor. So this data FEMFAT is using. Then the very next time, you don't even need to create the materials. If you and You don't even need to create the materials. You can directly import these things. Import, import, and go to your directory. Sorry, you can go to your directory and you can directly import these things. Press OK, and again you can go here and press OK. And these are text files, and this can be shared among your friends and in your team, in your organization, so everyone will use the consistent material properties. Okay, so this is how you can create the materials, and there are variety of material sets here. Suppose if you want to create wrought aluminum alloys, so you can go here and you can create wrought aluminum alloys. Uh, so this is how you can create the material properties in FEMFAT. Okay, there are wide ranges of material, and for each material you can see the SN diagram, SN curve, and you can also see the Hague diagram also for this. Okay, and this is how you can import the material, export the material. Okay, then the next question arises, like how to use different materials in our fatigue solver. Suppose you have a deck here and these are two materials. So this circular part is steel, and this part is our aluminum, that is casting. This is a machined part and this is a casted aluminum part. So firstly, if you want to use the FEMFAT, after solving the deck, you can again import the INP, and you can create sets here. So for sets you can type, uh, suppose I am creating a element set. So always you need to create the element set for the FEMFAT analysis. If you are having multiple materials, so you can type, you can create a set STFE410 and body 1, suppose. So I will switch this to elements, and, and by this one by attach. So each and every element is getting recorded in this set, and then in next set I will do aluminum casted component. Any name you can give it, uh, just for, but you need to understand the component, like which name you have given assigned the sets to those components. So this is this, and this is this body, and then one more set you need to create, that is first fatigue set, which will contain these two uh, all sets. Suppose there are two sets, so this will contain all the sets which we need to analyze. This should contain all the elements which we need to analyze. Okay, so these three elemental sets we have now. I will just uh, process this here. Suppose I have exported this. Once this is done, you can go to FEMFAT and you can go to FE entities. File format is ABACUS-INP, and you can read this. Okay. Once you read this, you need to go to groups. Okay, this is the total element count. So once you got into the groups, you can see like there are some materials, some sets which we have created, and in FEMFAT those are called groups. So you can just add those groups in the FEMFAT groups uh, to analyze for the fatigue. So I am choosing this first set. This is first group. This is aluminum cast form, and you need to tick this option, check this option, relate to elements in group, then click on add here. So this number of nodes have been added, and then you can go to FE410 body underscore body 1 and just click on add here. So this number of nodes will be added, and you can then select FEMFAT set which contains all the elements, and you can just select this. And by the way, whenever you click on this, the nodes of these groups are added in the FEMFAT group. Okay, then you can assign the stress data. For time being, I'm not doing it because I'm just showing the how to assign the materials. Okay, so these two materials we have created, or you can directly import this one. We have already seen this. Then you need to again define the load spectra that you can do. Then you need to go to node characteristics. Node characteristics is nothing but the uh, you can say like the material assignment of those nodes. Those nodes belongs to which material the FEMFET wants to know. So firstly, this group is aluminum casted comp. Okay, and you the material relevant material whatever we have imported is aluminum underscore casting. Then comes the main part, that is the surface roughness of this. So surface roughness of aluminum casting component, this is a casting component. Okay, this component is casting component. Then so surface roughness is cast is 200 microns. And what is the influence of surface roughness in endurance limit? Anyone from the basic experiments and from our textbook, we know that as the surface roughness increases, our effective endurance limit decreases. So uh, if uh, if a specimen without any notches or without any with a good quality surface will have more fatigue life. If you take a specimen with a rough surface finish will be expecting a less relatively less fatigue life. So casted components 200 micron, this will further uh, reduce the effective endurance limit. Then you can go to assign this material, this group Fe410, this is Fe410 material, and this is our smooth material. So is 60 microns is nothing but it is the surface roughness of a machined component. Okay, so this is a machined component. So surface roughness I put it 60 microns. This fatigue underscore set, you don't need to define any material here. Be careful with it. Okay, in the endurance now we can go to influence factor. So this influence factor, what is the use of this influence factor? So you need to like tick basic certain options here. So as we have used surface roughness, so the FEMFAT will adjust the uh, effective endurance limit. So you need to check this and surface roughness. Then in the last option, you can check this uh, mean plus amplitude unfavorable sequence as we have discussed it earlier. Okay, then you can simply go to analysis, output parameters. Sorry, you can go to analyze and you can select this fatigue underscore mod, and you can just click on analyze. Okay, so this is how you can uh, use this. You can use different materials in a single setting. So this set, what is the importance of this footing underscore set? This set allows us to solve for to solve for FEMFAT, to solve fatigue problem in a single run. So if I haven't created this fatigue underscore set, I need to solve individually. Once for aluminum casted component, once for Fe410. Now I can directly select this and I can click on analyze. It will solve for n number of materials. If I have created 10 materials, and I will put those all material elements in fatigue underscore set, and I will not define any material for fatigue underscore set except other groups. I need to define the materials, and then I will click on analyze for this fatigue set. All the material fatigue cycles, I will have this in the output. So this is how you can perform this. Thank you. Have a great day. Bye. Hi, welcome to Simulated Engineering. So today we will see like the use case of this constant stress. What is this constant stress, and in which scenario we need to use the constant stresses, and why to even use it, and why to even bother it about this. So, firstly, let's back to the constant stresses. Like constant stress, like is any type of stress which will be during the assembly of the component. Maybe like suppose there is a real life example like uh, during the assembly there are fewer nuts, bolted joints are there, and it needs to be tightened. So there will be a preload stresses will be generated in the component. So this might be the one use case of the constant stresses where constant stress will be applicable in this case. Then if you apply the variable load and try to calculate the fatigue, and you are not considering the constant stresses, then your fatigue life will be more, and in reality your fatigue life will be maybe 1000 or maybe 2000 or maybe 10,000 cycles less than whatever you will be calculating without the constant stresses, because the constant stresses are mostly in most of the scenario are tensile in nature, and that will lessen your fatigue life. So we need to introduce the constant stresses wherever it is applicable. So bolt pretension is one of the scenario where constant stress is applicable. The second might be your press fit analysis. During the assembly, if something we are press fitting it or something interference is there and we are press fitting it, then there will be stresses will be generated during the assembly itself. That's it. Some kind of residual stresses will be generated, and when you apply the and when it is subjected to fluctuating loading, then this stresses will play a severe role in your fatigue life, in the assessment of your fatigue life. And third, and maybe example will be like the screen example. It will have a certain uh, constant stress due to its self weight itself. So the weight from uh, the weight from here to here will be try to bend this crane, and you will have a significant tensile loading in this in the upper fiber, and this will be a constant stresses. This will be termed as a constant stress. This will be always be acting on the crane, and whenever you are pulling load and dropping it, then this cycle, this constant stress will be added to those. So this is one of the example of constant stresses. There are other examples also. So sometimes it is very critical to consider the constant stress in your fatigue assessment. So that is why there is an option in FEMFAT to use constant stress. So we will see one of the examples, live examples using Abacus as a solver. So before starting here, let's go to the whatever the solved ODBs I solved it earlier. So this ODB, like this is the first load case where I am just constraining it here in one to in all DOFs, and I'm applying a load here. So its animation is like this. This will be my positive load, and I will use the scale factor to use the negative load. I will use the scale factor in FEMFAT to use it as a negative load also. Means upper and lower, I will use the same ODB. If you don't know what is scale factor or how to use this scale factor. Just watch this video, which is at the top end. Now coming to what I solved for the constant stress. I will show you what I solved, and that is a very realistic load case. Uh, Let me open this ODB. It is opened. So what I am doing here is uh, I will play the animation, and you can see like it is reflecting in this direction, in the downward direction. Actually what happens in here is I am constraining it here and I am applying the load here. I am assuming like uh, there is some self weight, there is a small weight I am putting it here. So the weight of it I'm just applying as a load, and that will be my constant stress in this in this beam. And my pulsating load, my alternating load will be in this direction, will be in longitudinal direction. That is just, this will be my longitudinal load. Okay, so I will use this in FEMFAT. So let's start. So firstly is, we all know that is, I need to uh, just set the directory. I will set this directory first. So change directory, no, and you can put this, and you can just erase this. Okay, so let's start now. Yeah, so I will load my Abacus INP as I have solved in Abacus. You can even use Nastran, or you can use ANSYS, or you can use OptiStruct or any other solver, and you can solve in your fatigue. After getting the stresses, you can solve in FEMFAT. Then once this is loaded, you can go to groups, and you can just go to what is the component name. We need to check the component name auto 1. So let's get auto 1 and this, and just add this stress data. Now here I'll show you, like in the upper load case I will use post load, so it is loaded. In lower load case also I will use post load. Okay, and I will use the factor here, which will change this stresses to negative. Just I will put -1, apply. So it is changed to negative, close it, and in constant stress I will use my whatever the load which is causing the bending of the beam. So this is my constant stress. Okay, then I will go to material. I will define a material of steel which is having a, ultimate strength of 500 MPa. Okay, I will press OK, and then I will go to load spectra. I will use new here. This steps you guys already know. Then in node characteristics, you need to put auto, then this FE500, and this, as it is a machined part, I will use 60 microns as my surface roughness. In the influence factor, then you need to check the surface roughness option, and you need to also check the constant stresses options. Then in the blast you can use mean plus amplitude unfavorable sequencing effect. If you don't know what is this, you can watch this video which is here. Then uh, you can go to analysis factor, and you can just switch on absolute. This global is fine. Output is, I need to change it to hypermesh DMA file, and then report. Then analyze, I will go to auto, and I will go to check input data, is whether my input data is correct or not. So it looks okay. Then I will click on analyze. So once analysis is done, You can use either the FEMFAT visualizer or you can use the Hyperview itself. Yeah, so we will check our fatigue life now. So for this, you just need to load the DMA file and yeah, you will get your fatigue life here. So 1 byte damage is nothing but your fatigue. So just apply and you need to reverse this because we are more interested in minimum fatigue life and that should be the red color. Okay, and is all together red. Yeah, so it's all together red and I'm expecting like you will get your least fatigue life in here because due to bending you will have the mean stresses piling means sorry, the constant stresses piling up here and your pulsating fatigue, your pulsating load will give you the stresses everywhere because that is a normal stress. And so we will just put one value here. Let's see what is the value. We will mark one node here. Okay, let's uh, calculate the amplitude stresses and the mean stress. So mean stress I will just put for uh, 1052 node and it is 165 MPa mean stress and your it's approx 165 MPa and your amplitude stress is 141 142. So your mean stress is 165.2 MPa and your amplitude stress is what is the value we got 141.7 MPa. So we will try to calculate this values and we will further like we can further check it whether we have done the fatigue, whether the software has done the fatigue analysis correctly or not. So we will go to our model and this is by the way the node number 1052 and we will go to signed one misses. Just roughly I am calculating it. This is not the exact calculation but give us the, it will give the idea and yeah. So sign one misses you need to use corner data and advanced average as FEMFAT is using corner data with advanced average and so I need to annotate uh, 1052 stress 1052 nodal stress. Okay, 1052 and so uh, it is so this is by hyperview so it is one somewhere 142 okay MPa during your longitudinal load, positive load. Okay, and what about this one? So again we will do signed one misses advanced average corner data on. Okay, and we will try to calculate this node. Sorry, this is advanced average should be switched on, and we will try to calculate node number 1052. Sorry, nodal contour I want 281.9 281.9 MPa during constant stress. By the way, these are all positive. These both values are positive. So now how to calculate your mean stress? So we want to calculate the mean and amplitude stresses by using hand calculations to further verify our FEMFAT results. So here is the calculated amplitude stress. So amplitude stress is nothing but upper stress minus lower stress divided by 2. So upper stress is like longitudinal positive load, that is 142, and plus constant stress, which is positive of 281.9, minus then bracket. Then lower stress is, we have used the scale factor to make this as negative in lower stress. So it is minus 142 plus of this value divide by 2. The It comes out to be 142, which is nearly equal to 141.7. So that means that is amplitude stress is correct. And one more thing to notice here is amplitude stress is independent of your constant stresses. So whatever constant stress is, it will never increase or decrease your amplitude stress, but it will have a significant increase or decrease in the mean stresses. So we will see next. So if you see that mean stress is nothing but your upper stress plus lower stress divided by 2. So upper stress, if you calculate it, it is 142 plus of 281.9, and lower stress is same here. So it comes out to be 139.9 and 423.2. This is just, and I will, if you calculate this, you will not get 164.95, but you need to take into mind like these are just the stresses from linear material properties. We have used the plast option. So we have used the plast option. We have used the plast option. So this stress, if you see this is the yield strength of the material. So this stress is well above 284.5. This is well above yield limit. So we need to convert it into Newber stress. That's what FEMFAT Plast is doing. So if you convert into Newber stress through hand calculation, it is coming out around to be 190. And if you calculate that, your mean stress is somewhere around 165, which is nearly equal to mean stress of FEMFAT stresses. So we have calculated the amplitude and mean stress from the ODB abacus stresses, and we have again evaluated the FAMFAD mean and amplitude, and both are nearly equal. That means whatever we are doing, it is correct only. And second thing, one may ask like why you have not used Newber correction method here in amplitude stresses. Even if I use Newber correction here, whatever the value this will make, the same value this will make, and it comes out to be 142 only, because this and this will get cancelled, and again your amplitude stresses will be equal to this value only. So this is how you can calculate amplitude and mean stresses. And even if you have doubt, if you are unable to calculate the Newber stresses, what you can do here is, uh, I will tell you what you can do here is, you can simply switch off this option called blast. Then your results will be not be correct, but your mean stress and amplitude stress calculation will be quite simple, because whatever the, it will not convert the linear stresses into Newber stresses, and whatever the calculate, your calculation will be quite simple. You don't want to convert into Newber stresses, but your fatigue life will be lot less if you are not using blast and you are using linear material properties. Thank you. Have a great day.
Hi, today we'll see like how to get the detailed results in FEMFAT. If I suppose I solve the problem and I want to uh, get the detailed results of each and every node, uh, the Hague diagram of each and every node after my analysis, or the SN curve of each and every node of the after the analysis, then how to do it. By default, the FEMFAT will display at the critical node only. Uh, so I have loaded one INP file here as for the file format to get the groups, etc. And in the group I have selected all. This is just for display purpose. And stresses I have selected upper lower, two files are there. And in material data I just put some random material. This is anyways steel of 320 MPa, ultimate tensile strength of 320 MPa. And then loads, other things are as already discussed in my previous video. And then if I press here, the analysis parameter, I have selected the all the nodes, means absolute stress 0 Newton mm square I have put. So whatever above this gets analyzed. So in the output I have put hypermesh results, that is anyway optional for this analysis. And then I just put all, and then I will click on analyze. Okay, so my analysis is done, results are there, and you see the critical node is 307, that is the max damage node, means I will be expecting the minimum life here. So if you go to the Hague diagram, only the most critical node is 307 I can see. This is the Hague diagram of material, and this is the updated Hague diagram for this node. So how to get for any other node? If I want to query for 308 or some other node in my model, I'm more interested towards that node. Then how to do it? So in FEMFAT, you go back to groups here, and there is something called a detailed results. So if you click on it, it will basically analyze all the nodes. Means it will basically draw the Hague diagram for all the nodes, so it will store this data also. So I'm just clicking on detailed results. It will increase my analysis time, but uh, for uh, uh, proper, what can I say, for proper tracing of each and every node of Hague diagram, I will use this. So my analysis is done, results will be same as it is. There will be no change in the results. Makes you you need to make a note, there will be no change of by using that option in the results. The only change you will get is you will get some additional outputs, like in Hague diagram now. uh, with 307 node number, which is our critical node number, there are all other node numbers will be there. Suppose node number 1, if I click on node number 2, then this Hague diagram will get changed based on the nodal stresses. So if the node is 200, this is my Hague diagram, and if the node is suppose 301, this is my Hague diagram. So this way you can get the Hague diagram of each and every node, and you can understand what's going on and uh, how to give some design suggestions on the basis of this. uh, Thank you, have a great day.
Spot welding is a process of joining two metal sheets by applying heat and pressure at small points between them. It is widely used to model in automotive industry for strong reliable connections. But the question is how to model this in finite element analysis to predict their behavior under load. So there are several ways to model spot weld in FEA, but for force-based method, there are two popular ways. First is the beam method, beam element method, where your beam of dia of the basically I'm assuming like the dia of the spot weld will be 6 mm, and on the basis of that I am modeling one beam, and that beam is connected via RB3 to these elements. So one is the beam element method, and second is, which is little more popular in automotive industry, is the ACM method, or we call it as hex RB3 method. Basically what you do here is you create this uh, spot welds using ACM technique. So basically, uh, this you can choose the number of nodes here where you want the spot weld, and then you can choose the component. This is it. we used to create in hypermesh, but in any other software there will be one method. So basically what it does it is it create one hex element, and this hex element is created to RB3s, and RB3 is connected to this plates. So in this way, we used to create these spots. So basically, two popular methods are the beam RB3 method and hex RB3 method. So for calculating fatigue, we are using force-based method. There are two methods to calculate fatigue in spot weld. Basically, stress-based method, and second is force-based method. Force-based method is convenient and easy to use. So we don't want to go into much into the modeling details of nugget of this spot. That's why we are using here force-based method. So force-based method here we are going to use. So suppose these two sheets are joined by a spot, then we will request the output, nodal output, force and moment nodal output from the software, and then the FEMFAT is going to use the stresses used to calculate the stress from those force and moments of those of that spot nugget. And basically, if we are using abacus or maybe OptiStruct or Nastran, we need to request this outputs, force and moment outputs. So basically, that syntax is enforce. We need to request enforce in the case of abacus. And if we are using Nastran or Altair OptiStruct, we need to use GP force there. So suppose this is the structure I am going to analyze using FEMFAT, do calculating the spot fatigue. So basically there are two spots here, and I have created few sets here. So FE510 is this set, FE300 is this set, and the most important thing is uh, you need to do is like this is the abacus deck. So abacus, you need to put FEMFAT spots as the number of as these two elements, hex elements of this spot. If this is a beam, then you can put beam in that element EL set. Okay, and finally there is a fatigue set which contains this all. Okay, so once this is clear, I will export this deck, and then I will solve this in ODB, and then I can import this in FEMFAT. So in FEMFAT basic, I will read this INP. So once you will read this INP, you can see like the spot welding points will be there. So this is 4. Why it is 4? Because if you see like here, here there are two spots, okay, and these are two T spots, means uh, these are connected to two plates. So this will have 1 point here, 1 point here. So these are having basically are one spot is joining two plates, and this spot is again joining two plates. So this spot welding points force will be 4. Okay, and you have defined this in FEMFET underscore spot. So if I have defined only one hex, then only 2 points will come, but in this case I have defined both hex, so this both points will come. If this set is not there in your INP file, then the FEMFET cannot be able to identify which are the spots. This is it, by the way, this is in abacus. Okay, so now groups. So groups, I can add these groups again, okay, which I have created, and fatigue set. Okay, the stress, I can load this stress. Okay, so once the stress is loaded, you will see the number of spot elements is force theta is equal to 2. Because I have requested n force here, I will show you. Requested n force here. So if you see this INP file, if you read this and see this INP file, then if you see this.
element star element output element set FEMFAT underscore spot, and both have requested enforce and enforce SO. Enforce SO is basically for beam coordinate system, and enforce is for the your global coordinate system. So it is good to request both, as enforce SO is more useful if you are designing spot welds in your FEM model using the beam element method. And enforce is useful if you are using spot hexa, um, if you are using spot weld as hexa arbitrary. Okay, so once this is clear, we will go to here again, and then we can define the materials. So here there are two materials I have inputted. Okay, and by the way, one more thing is like the spot properties will be same. Like the spot will always be your linear steel model. I will show you. The spot hexa will have the properties of your steel, linear steel. Okay, and this one cycle I've created, as we have already know this, and then in nodal characteristic, this is the main uh, thing. We will assign the materials here. So FEMFAT 300, I will do 200, and let's for here 60 microns. FEMFAT 510, I will assign as 500 and 60 microns. Then FEMFAT spot, you can assign here any material, but it is necessary to assign some material to FEMFAT spot in FEMFAT basically. So I will assign this material. Then in influence factor, general factors, you can use copy this properties blindly, and I will put mean plus amplitude and favorable sequencing. And then in spot, you need to check this box to enable this spot. If you don't check this box, this spot will not be solved. So you need to check this box, and then go to spot force, again check this box, sign one message you need to select, and then you need to connector diameter, you need to select it from FE geometry, and I have used the connector diameter of 6 mm. Okay, and connector material you need to select not from the connector material which we have defined is from the FEMFAT. We will as we will decide the connector material from the seat material. So how it is taken from the seat material? So basically, between these two plates, which is having the lower material properties, means weaker material properties, this pot will take that material property in FEMFAT. Okay, so again we will go to analysis parameters, and here the settings are already mentioned in my previous video, and then in here in hypermesh results we can just use this DMA. So once this analysis is done, we will open this INP and DMA file in my hyperview, and then I will plot one by damage. Basically, I will reverse this contour. Let me rearrange this uh, color scale. Okay, as you can see, like uh, you have the least damage here, and this spot is doing nothing. Like it is safe, and here you have like the life is very less. And one more thing about a spot I want to showcase here is, if I go here from at a spot, let me isolate this. You can even plot this, the life of the spots. So this is how you can do the spot weld in Abacus. So this method of spot identification using set uh, will work in Abacus, but but for OptiStruct and Nastran this may not work. So because the OptiStruct and Nastran solvers uh, store their set informations in the form of numbers and property informations also in the form of numbers. Then how to do this? So basically you can simply change the property ID of your hex. uh, Basically I need to change the card image also here to something called as p solids. Okay. So basically you need to change here to 2 lakh. So your property ID of your hex will be more than 2 lakh, between 2 lakh to 3 lakh, and for beam it should be uh, between 1 lakh to 2 lakh. So this is how you can define your spots in Nastran and Optistruct. Hi, welcome to Simulated Engineering. Today we will see like how to create a fatigue block cycle in FEMFAT. So first step is like to input the FE entities, groups, stress data and material data. Then you will go to load spectra, and in load spectra just click on new here, just press OK, and the number of steps, if there are 3 steps in fatigue cycle, then you can create 3. If there are 4 types of fatigue cycles, 4 types of different 4 types of different cycles in your fatigue. Suppose one is going to P plus P to minus P, second cycle is going for plus P to 2p to minus 2p, then you can create in that fashion. So in current scenario there are 3 types of steps here, so I will press 3 here. Then first step is going for plus p to minus p load for about 300 cycles, and I have solved the abacus ODB for plus p to minus p, and I will use the same ODB for second step also. Second step is nothing but plus 2p to minus 2p, and it is going for 200 cycles. And here I need to put 2 here, and I need to put 2 here also. Then the third step is plus 4p to minus 4p, and load, and it is going, and it will test will be conducted for 10 cycles. And so I will put 4 here. What is block cycle in detail? So suppose there is a fatigue test we have performed in this component, where first step is like to load the component from plus P to minus P for 300 cycle, and then we will stop the test and we will load the same component in step 2. We will basically increase the load to plus 2P to minus 2P for 200 cycles, and after this test has been done, then we will load the same specimen to step 3, which is plus 4p to minus 4p load for 10 cycles. And if someone asks you before even testing, like simulate and let us know will this product sustain this fatigue load or not, and you need to create the block cycle in FEMFAT to know whether this is above one block cycle or not. If it is above one block cycle, that means that your component will not fail under this cumulative damage test. And if it is less than one block cycle, then you can say like your component will fail under this cumulative damage test. FEMFAT uses this minor rule to calculate this block cycle fatigue. Then you may ask what is minor rule. So let us go to the next slide. Like minor rule says that basically it calculated damage, and it says that damage is cumulative in nature, and every fatigue cycle have its own damage. And when the total accumulative damage is equal to 1, then it says failure occurs. So damage should always be less than 1, so that we can say it has passed one block cycle. So and the equation of minor rule is quite simple. It says that damage is cumulative in nature, and it says like if for a particular fatigue load, the n is the total number of cycles the material can survive, and small n is the number of cycles for that load that it is going during its lifetime. So it says that the summation of Ni divided by capital Ni is equal to damage. So this is how it calculates the total fatigue life, total damage, and the reciprocal of damage is nothing but your fatigue life. So we'll see here by one example. So suppose there are two cycles here. If you see that, so there are two cycles. One is like N1 cycle, which is going for two cycles, and this is N2 is going for two cycles here. And this small gray color cycle, its total life is four cycles, and this big cycle, this sine color cycle, its total life is six cycles. Sorry, this sine color cycle is total life is four cycles, and this gray color cycle the total life is six cycles. If we go like the cycles up to failure, and in actual loading condition we have got two cycles this component has run for. So we will calculate damage. D1 is 2 by 6 and D2 is 2 by 4, and it is self-explanatory. So it is coming out to be 0.83. So total damage is less than 1. That means it will go above one block cycle. It will go like total block cycle will be 1 divided by 0.83. And if you see the second example, in this, the small gray color cycle is having, in actual condition, it will run for two cycles, and the sine color will run for three cycles. So in that case, it will come out to be the damage will come out to be 1.08, which is the damage is more than one. That means this component will not sustain this loading condition. And if you want to calculate the fatigue life cycles, it is nothing but 1 by total damage. That is how FEMFAT used to calculate it. But suppose your block cycle consist of these two types of load. Suppose those are completely different in nature, then this method cannot be used because it just depends on your scaling of your amplitude stresses and your mean stresses. So you can't directly use FEMFAT basic to create the block cycle. So how to do it in such cases? How to create block cycle in such cases? So then there is one simple way you can use like this. This can't be used in directly in FEMFAT basic, but in FEMFAT basic you can solve each load case independently in FEMFAT basic like step 1 and step 2, and apply minor rule uh, in your post processor, or you can directly use transmax or channel max. So this we will see in our next video. Thank you. Have a great day.
Hi, today we will see like different file formats in FEMFAT which are used in FEMFAT or which are generated during the analysis when the results file also. So first is the .bdf file or any other input file. So that contains our FE information and which we just input it our in FE entities. So it will identify this nodes, elements, sports, etc. So we will check once now what is CID file in FEMFAT. So it is check input data file. So if you go on and hit like check input data,